Hi, this is John, and this is lecture 4 for week 5 of CS 1030. And if you remember from the last lecture segment, we looked at recovering the value that's stored in a number that's represented in binary or representing in base 2. And in this lecture segment, we're going to do the opposite. We're going to look at an algorithm for taking a number and for converting it to binary or base 2. So let's talk about that. So given a number such as 18, and here I've represented 18 in two different ways. I've represented it using tally marks, so you can see there's 18 marks here. And I've also represented it using base 10. So given a number such as 18, the question is, what's the equivalent value in binary? So here's a binary number where we don't know any of the bits that are stored here, but we have some places where we can fill in the bits. It's in base 2. And so the goal is going to be to recover this binary representation for 18. And the reason on the slide that I've showed 18 written two different ways here is I would like to emphasize that this algorithm isn't for converting base 10 or some other base into base 2. The algorithm is for taking a number, which remember, abstract numbers are baseless, they're just numbers, for taking an abstract number and converting it into base 2. Okay, so let's look at how it works. And it's basically pretty easy. So given a number, and we're going to call it n here, the first thing we need to do is find the largest binary digit whose value is less than or equal to n. And by binary digits, what I mean here is if we had a binary number with a 1 in only a single bit position, the question is what values could we get? And we'll look at an example of those on the next slide. So let's not worry about that detail right now. So we're going to find but there's going to be a number, which is the value of the largest binary digit whose value is less than or equal to n. And once we found that number, we put a 1 in the bit position corresponding to that binary digit. And the 1, when I say put a 1 in that position, this is a 1 in the final answer in the binary number that's the output. Now we subtract the value of that binary digit from n. And if the new n is 0, we're done. Otherwise, we repeat the process. And one thing you should sort of convince yourself of here is that n can never go negative, and it's because of this condition here, because the value has to be less than or equal to n, so n can never become negative. And another thing we would like to sort of understand is that this will always terminate. This algorithm always finishes. It always makes n eventually go to 0. And the sort of proof of that is not so easy, so I'm not going to worry about it right now, but it is the case that that's true. Okay, so when this algorithm terminates, because n finally became 0, we're going to end up with 1s in one or more different bit positions. And that's our final binary number after we fill in the blanks with 0s. So there's 0s anywhere that this algorithm didn't put a 1. And one thing to observe about this algorithm is it always works from left to right. It always puts, the first 1 that it puts into the binary number is at the highest bit position that's going to get that's going to get a 1 at all. And all the subsequent ones go to the right. So it basically moves from the left end of the binary number to the right end. And later, in a different lecture segment, we'll look at a conversion to base 2 algorithm that goes the other direction. But we don't have to worry about that right now. Okay, so let's go back to this algorithm and let's watch it work. So the thing to do is to think about the numbers that you get, the numbers that you can get, use it from binary numbers that have a single 1 in them. So if you have a binary number that has a 1 only in the 1's place and 0 everywhere else, the value of that binary number is 1. If you have a binary number who has a 1 in the 2's place and 0 is everywhere else, the value of that binary number is 2. If the binary number has a 1 in the 4's place and 0 is everywhere else, the value of that resulting binary number is 4, and so on. So basically, we can recover all the powers of 2 this way. So what we want to do is find out of this sequence of numbers the one that is the one that's the largest without being larger than the current value of n. And the current value of n here is 13 because we just started the algorithm. So one thing we could do is start with 16, which is bigger than n. And if we actually, so that's not really what the algorithm said to do, but it doesn't really matter because that's going to produce the same result. So if we started with 16, that would give us a 0 at that position because 16 is not a component that's going to go, that goes into 13. And it can't because it's larger than 13. Because remember that positional number systems always use addition to add up the components of it. And so 16 can't possibly be a part of it. Okay, so the largest binary digit that's value is not larger than n is 8. Because 16 was too big, so 8 is the largest one that actually works. So what we're going to do is we're going to end up putting a 1 in the 8's place of the resulting binary number that we're outputting to the user, or they're storing somewhere. Okay, and so now we subtract 8 from n, from 13, and that gives us 5. So the new n is 5. And now the question is, now we start the algorithm over again. So now the question is, what is the binary digit whose value is the largest but without being larger than 5? And it turns out that that's 4. So we put a 1 in the 4's place of the result of the output binary number, and we subtract the value of this binary digit from n, so that gives us 5 minus 4 and leaves us with 1. Okay, so now in the 2, now we'll see that 2 isn't going to be a component of this binary number because 2 is greater than 1, so we're just going to end up with a 0 in the 2's place, and we don't subtract anything in that case. And now finally, we can see that the largest binary digit which isn't greater than 1 is 1, so we're going to get a 1 in the 1's place, and we end up with 0, and so so we're done. The algorithm terminates, and the resulting binary number is 1101. Of course, we could also say 01101, but we usually suppress the leading zeros. So the answer for what is 13 in binary is 1101. Okay, and this algorithm will work for any positive number, or for any number that's 0 or larger. Okay, so that's what I wanted to show you in this lecture segment. And I just want to ask one question before we finish up here, which is that we looked a little bit at numbers using the tally system, using tally marks. And the question I'd like to ask you to think about is, what base is this number system? And I'm not going to answer. This is something you should think about. And if you want to know the answer, we can talk about it in recitation, or you can talk about it on Canvas or something. Anyway, I'd just like you to think about that. Thank you.